Hi, welcome to When Do Gaussian Errors Arise? Let's say we're going to measure a quantity that we'll call Q. We'll call the true value of this quantity Q true, and the value we get when we perform the measurement Q measured. Due to measurement error, these will not be the same. There are lots of sources of error that can push our measured value, Q measured, away from the true value. For example, our measuring device is not infinitely precise. There will be statistical errors in our experimental data. The measurement device can change with conditions such as temperature and age. And we can have statistical errors in simulations that we use for data analysis, etc. We don't know the values of these errors for a given measurement. If we did, we can add them up to get the total error, and that would mean we knew the true value of the quantity we're measuring, which we don't know. In a given measurement, each of these sources of error will push Q measured either up or down compared to Q true. So here we have Q true, and we have one of these sources of error, signified by the yellow arrow. The source of error can push Q measured up from Q true, as shown here, or it can push it down from Q true, as shown here. These sources of error will be of different sizes and go in different directions. The total error, Q measured minus Q true, is the sum of these effects. So here we show that the result we get in a given experimental trial, Q measured, is equal to Q true plus the sum of all of these errors represented by the sum of these yellow arrows. Okay, so let's now look at the conditions under which Gaussian errors approximately arise. Let's say that there are many of these sources of error. We'll number them. So for example, source 1 may be the effect of temperature on the measurement apparatus, and source 2 may be statistical error in the experimental data. Right now, let's just look at source 1. Okay, here's source 1. And let's say we did the experiment many times. We did many experimental trials. Here we're going to take error source 1 to be sensitive to fine details of the experiment, which change with each trial. So its size and direction change from one trial to the next. If we were able to measure this error source over many trials, we would see that it has a distribution and see its typical size. But in a given trial, its size and direction are random, drawn from that distribution. So sometimes it pushes the measured value Q measured down, and sometimes it pushes it up. Sometimes the effect of this error source is small, like shown here, and sometimes it is large, like here. And we are taking the trials to be independent. The size and sign of the error from source 1 in one experimental trial doesn't affect the size or sign in the other trials. We are also taking the average value of this error source, averaged over all trials, both up and down, to be 0. On average, it doesn't push Q measured up or down. We're not saying that its absolute value is 0, just that over a very large number of trials, it doesn't have a bias to push Q measured up or down. Next, we're taking all of the different sources of error to be independent of each other. So take two different sources of error. For example, here, sources 1 and 17. If they are independent, the value that one takes in a given trial does not affect the value that the other takes in that trial. So here, sources 1 and 17 don't affect each other. We take that to be true for all of the sources of error. Lastly, we're going to impose a requirement on the relative typical sizes of these sources of error. And note that we aren't talking about their sizes in a particular experimental trial, just their typical sizes. We're going to require that the total error not be dominated by one or a few sources whose typical size is much larger than the rest. If the most important sources of error have similar typical sizes, and if there's a bunch of them, then that's the situation we're looking for. So if a situation like this one is typical, where we don't have one or two sources much larger than the rest, then that's the kind of situation we're talking about here. We don't want a case where one or two or three of the sources are much larger than the others. So if one or two sources tend to be much bigger than all of the rest, that's not the situation we want. Under these conditions that we've laid out, the different sources of error will have a tendency to cancel each other out to a large extent. In a given experimental trial, some will push Q measured up and some will push it down. This is the scenario where the error distribution starts to resemble a Gaussian. This is far from obvious. We'll see how it happens later. For now, we're just looking at the conditions under which the Gaussian behavior arises. How well it resembles a Gaussian distribution will depend on how many competing sources of error there are and their relative typical sizes. In future videos, we'll see just how well the Gaussian description holds up under different conditions. But here's an important point. Situations where there are a bunch of independent sources of error of similar size show up in nature, at least approximately, pretty often. So while the situation we've described here might seem a bit complicated or artificial, at least as a useful approximation, it shows up quite a lot. Let's see why it shows up more often than we might naively guess. Let's revisit this situation where one or two sources dominate over all the others. Sometimes we see Gaussian-like behavior even in this case. Why is that? Sometimes, upon closer inspection, we find that that dominant source of error is actually composed of many smaller, independent error sources, and that the conditions for approximately Gaussian behavior are actually fulfilled. So errors being approximately Gaussian distributed actually happens pretty often. Lastly, let's note one more thing. We described Gaussian errors in terms of what would happen if a measurement were carried out over many trials, and those trials were independent. But in practice, a measurement may be performed only once or a few times. Additionally, if a measurement is performed multiple times, those trials may not be independent. There may be systematic errors that are common to all trials. In this case, more detailed studies may be needed to draw the correct conclusion from the set of measurements. Okay, let's briefly mention what we'll see next. We'll try to see how Gaussian distributed errors arise by doing some simulations. Specifically, we'll look at a series of simulations of random walks. A random walk is a mathematical model of an object that moves randomly in one direction or another. We'll use it to model sources of error that push a measured value up or down. So basically, we'll model a source of error that pushes Q measured down as a step to the left, and a source of error that pushes Q measured up as a step to the right. The first simulation we'll look at is one of a particularly simple random walk. This won't simulate measurement errors in a realistic way. It will be too crude. But we will get a first look at Gaussian-like behavior. After that, we'll make our simulations more sophisticated and produce more realistic models of measurement errors. We'll see the Gaussian behavior show up much more clearly than in our first simulation. We'll also see under what conditions the Gaussian description models measurement errors well, and also when it doesn't. We'll also relate our simulations back to measurement errors, discuss the limitations of the Gaussian description of errors, and talk about the interpretation of a measurement reported with a Gaussian error bar.